Okay, it's recording. So let's keep on talking about. I hope this is the sort of the final lesson where I talk about equilibrium. Well, conditions of equilibrium. Then we're going to have to find a way to establish how to find the composition of equilibrium of a reactive system. Let me just close some of the arguments that I was making the other day, okay? I hope they're not too confusing, okay? But you may have noticed that we're really using very, very few concepts. In particular, if you remember, we had talked about conditions of equilibrium, right? And we had given or found essentially two, because the fundamental equation is actually invertible. We can write down an entropy-based condition of maximum entropy for an isolated system. Or if we invert the fundamental equation and express it in terms of an energy-based fundamental equation, then we have a minimum of internal energy. Here it is. Tell me if you can't see, yeah? At constant entropy, okay? Now, really, we want to get rid of either isolated systems or the constant entropy systems and open the possibility, because we've defined so many thermodynamic potentials that we can use, enthalpy, Gibbs energy, etc. Maybe they're useful in particular systems, okay, that are not just isolated or a constant entropy, but they could be, for example, more practical systems, like systems that I keep at constant pressure, or at constant pressure and temperature, okay, that are still, for example, closed, that don't exchange matter. And this is where essentially we define this kind of trick approach, which involves the reservoir. So we've always talked about composite systems, right? Systems that have some sort of internal constraint, okay? And if I release it, I want to know exactly what the condition is, where the system evolves to, right? Well, the reservoir is essentially a very, very big, ideally infinite system that surrounds essentially our system of interest, okay? So this is the system that we want to establish the equilibrium condition for, okay? And that we will keep, for example, at constant pressure. And the other system is the reservoir, okay, which we call, well, we indicate with a superscript R, okay? This is the reservoir. The overall system here is your composite system, essentially, okay? So one thing that we can do, for example, is suppose that we're interested in a constant pressure system, okay? So this system of interest, okay, we will keep at constant pressure. How do we do this? Well, we will have to choose wisely our walls around, okay? So I can choose these walls, okay, as being, for example, isentropic, okay, impermeable, so that there is no leakage of mass, for example, and flexible. Why do I choose flexible walls? Well, so that I can keep the pressure, okay, constant. So essentially, I will keep the pressure equal, okay, to the pressure outside in the reservoir, and this will be constant. Okay, so it's like having a piston that will let the system expand or contract so that the pressure is always constant. Now, the nice thing is that because the overall system is isentropic, okay, that's how I defined it, okay, I can use the minimum of internal energy, okay, constraint. So overall, the equilibrium condition is this, okay, where I'm summing now the internal energy of the reservoir plus the internal energy of the inner system, okay? So again, I will have to essentially express this condition here, okay? And the way I do this is I will express UR somehow, okay? This is essentially DUR plus DU equals 0. I want to get rid of all the reservoir, essentially, quantities, okay, that I don't know and I'm not interested in, because I'm really interested in only the inner system, which is my system of interest, okay, which is indicated with quantities without the superscript, okay, S, V, and N. So let's express the reservoir DUR, so the change in internal energy of the reservoir. We know that we can write it as TR/DSR, so TDS, okay, minus PdV, of course, always with the superscript, and the sum of the chemical potentials and DNR, okay? This is DNR, so mu I and DNI are the chemical potentials and the change in composition of the reservoir, okay, superscript R. Now, it's impermeable, okay, both here and here, so clearly there is no change in composition, okay? Also, okay, because the inner system and the outer system are isentropic, we can say that DSR is equal to 0, so this term is also 0, and as well as DS is 0, okay, because this is isentropic and this is isentropic, okay? What about this term here, PdV? Well, the interface here, walls, are flexible, right? So whatever expansion, okay, you undergo in the inner system, this is going to be a compression in the reservoir, right? So essentially, dVr is equal to minus dV. So if the reservoir, for example, contracts, if the inner system contracts, the reservoir expands, okay? And in order for the pressures, okay, to remain constant, okay? So PR is equal to P. So at the end of the day, we can express the internal energy essentially as minus PdV. Okay, that's what we can express it as. And so, if we go back to our condition of equilibrium, which was the change in the total, okay, internal energy, this can be expressed as DUR, which is minus PdV, okay? In fact, sorry, there is a plus here simply because there's a minus here, right? So it's PdV plus du, right? So, and P is constant. So this can be expressed as very simply as U plus PV, which is enthalpy, okay? And that must be equal to 0. So, long story short, we have translated essentially the condition, the old condition of equilibrium here, using the trick of the reservoir, into the fact that the condition of equilibrium for a constant pressure system is a minimum of enthalpy, which essentially means the fact that if you keep the pressure constant for an adiabatic system that is also isentropic, clearly, the enthalpy remains constant, which is something that I think intuitively we know. Now, could we have done this a little more simply? Well, in fact, yes, because if you write down the differential of enthalpy, okay, which we had done some time back, it's TdS plus VdP, okay, plus the sum of mu I dNi. Well, it's pretty clear that for an isentropic, impermeable, you see these and constant pressure system, well, dH is equal to 0, okay? So that, in some sense, tells us that the enthalpy is the right potential to use in the case of constant pressure system, okay? And we can go on and on with these examples. For example, suppose that we have a constant pressure and temperature system. A system that we want to keep at constant pressure and temperature, okay? This is, for example, a reactor, a chemical reactor that we keep at, for example, at atmospheric pressure in a laboratory, and we surround it by a dithermal wall, a cooling jacket, sometimes it's called, which can subtract or add heat so that the temperature is always constant, okay? So what are the walls? So now I'm talking about this inner system here, right? This inner system here. Now I have to choose wisely my surrounding walls. And as I said, I need to pick them as diathermal, so no, not adiabatic, so to keep the temperature constant, okay? Again, I have to choose them flexible to keep the pressure constant, okay? And impermeable, so as to not exchange matter. I still need to impose this condition here, okay? Sorry, equal to 0. And I have to essentially express DUR, okay, in terms of quantities that are not the reservoir quantities, but are actually the inner system, the system of interest quantities, okay? So again, I rewrite the whole thing. T DSR. I hope I can, again, my handwriting, not sure if it's improving, but it's not the easiest of things to write with this thing. So this is I, R, R, I, okay? This is the general expression. All we can say is that dN is 0 because it's an impermeable system. There is no communication between the reservoir, so the outer and the inner wall are impermeable, and so there is no change in composition. The overall system, again, we know by definition is isentropic. The overall, okay, system. So all we can say here is that ds is equal to minus ds, actually dsr is equal to minus ds. okay? As before, because the inner walls of the system of interest are flexible, again, dVr is equal to minus dV. So you see what I'm doing. I'm trying to eliminate I'm trying to express all of the reservoir quantities in terms of the inner quantities. Then we said that we chose the walls so that the pressure is constant. So there is equilibration between pressures and temperatures. Okay? Between the reservoir and the inner system. Okay? So DUR, if I substitute all of this stuff here, ends up being essentially, well, I substitute for DSR and T, I get minus DS, so it's minus TDS. And again, here it's plus PDV. And you see so that I've expressed all of the DUR, okay, all of the reservoir internal energy in terms of quantities of the inner system, okay? And so now the sum of the variations of internal energy of the inner and outer system, I can write down as du minus TDS plus PDV, okay? Which is essentially the differential of U minus T and P are constant, okay? Remember this, plus PV. And if you remember what this is, it's the Gibbs energy. So you see now, I hope that these thermodynamic potentials come in very handy when you are referring to particular systems that you're keeping in certain conditions. For example, in this case, the Gibbs energy tends to be quite useful for constant temperature and pressure systems, which are in fact systems that are of practical interest in the laboratory. Okay, it's not that I can keep, for example, a system at constant entropy. I don't have an entropy meter. Okay, and so the minimum of internal energy now for a constant pressure and temperature system translates into the minimum of Gibbs energy for constant pressure and temperature systems. Okay, so if you go back with your memory, we have overall 4 specialized kind of conditions of equilibrium. For isolated systems, we maximize the entropy. For isentropic systems, we minimize the internal energy. For constant pressure system, generic constant pressure system, the enthalpy, and for constant pressure and temperature systems, the Gibbs energy. Again, I could have skipped this whole thing by just looking at the differential, and this is what's usually done in conventional thermodynamics. Okay, so we're adding a little bit more, I hope not confusion. Okay, I think it's, to me, I think all of this approach is a little bit more logical than the old kind of inductive approach. But anyway, maybe it's only me. So the if you look at the overall dg, okay, you could have essentially substituted. So if I read here, I substituted du. So let's write it again. Du minus TDS. Yeah. Sorry, there is a little glitch here. If I okay, here. Du minus TdS. So I'm just rewriting this. Okay, in full, minus S dt plus PdV plus VdP. Okay, if you substitute for du, du, TdS, etc., minus PdV, okay, plus the sum of mu I dni, okay, dg comes out to being essentially minus S dt plus VdP, okay, plus the sum of mu I dni, okay, all in terms of the inner quantities. And clearly, for P and T constant, these go, okay? And so we're left with quite an important quantity, which is this guy here, okay? So for clearly for constant temperature, pressure, and impermeable systems, okay, we know that this is 0, okay? Now, try to follow this for a second. Suppose, however, that we always keep the temperature and pressure constant, okay? That's a fact. So these two terms are always 0, okay? If we keep the composition also constant, then also this term is 0, and this is trivial and boring, okay? But suppose that I perturb the system, okay? Now, remember what the perturbation of a system is, okay? Playing around with constraints, okay? Now, what do you mean by constraints when you're talking about a composition? What do you mean about perturbing a system when you're talking about a composition? Well, composition can be perturbed. Guess what? Through chemical reactions, okay? This is the first time I have introduced this concept, okay? Molecular species will tend to change into one another, react, okay? And also mix, okay? Together. Now, also mixing, okay, from two subsystems will yield a different DNI in one of the subsystems, okay? Now, chemical reactions really do this, however. They will perturb your composition. So clearly they will introduce a certain DNI that's not 0. So in general, the change in Gibbs energy, we can express it at temperature and pressure constant, always as the sum of the chemical potentials times DNI, okay? Again, for an impermeable system that doesn't change in composition, this is 0, okay? But if we perturb the system through chemical reactions, okay, and then we let, for some reason, the system evolve by itself, okay, this condition of equilibrium must kick in. And this is the second postulate, okay? If we remove internal constraints, okay, there is a maximization of entropy, which at constant pressure and temperature translates directly to a minimization of Gibbs energy. Okay, so what this is telling us is, I give you a constant pressure and temperature system, chemical system, okay? I can drive it into any composition, but, in fact, I can't, but suppose I could. But if I let the system evolve, okay, spontaneously, then the system will evolve in order to minimize the Gibbs energy. So this will be true, okay? So the system will move spontaneously, okay? Sorry, these secondary lines you have to disregard. It's just my pen that's not working properly. So the spontaneous evolution of any chemical system, okay, at constant temperature and pressure, is that to drive the composition towards a minimum of Gibbs energy. And at the end, when dG is actually equal to 0, then it means that we have reached the equilibrium point. Okay, we have reached the chemical equilibrium point. So, a long story just to come to this final little piece of result. It turns out, so again, let me write it here. So minimum of G at constant temperature and pressure, well, translates to the fact that the condition of equilibrium is actually this. Okay, this is the condition of equilibrium. And this is the spontaneous direction towards which the system evolves, okay? It turns out, and this will come a little bit later on in the course, that if I can express these terms, okay, the chemical potentials, well, then maybe I have a chance of actually really come up with some equations, which can solve my problem of actually finding the equilibrium composition, okay? But first things first, we don't really know yet what a chemical reaction really is, okay? And again, if I go here, I really must first introduce some concepts regarding the only way in which chemical systems can be perturbed, or in other words, the only way in which we can devise a way of changing the composition of a chemical system, okay, which has to follow some strict rules, okay, namely the conservation of atoms. And I won't say it now because I will say it again many, many times. Don't make the mistake now that we'll talk about chemical reactions of considering these reactions as you usually do as collisions between molecules. So let's first of all start introduce the concept of chemical reactions. Can you hear me?
Sì, tutto bene.
Okay, good. Okay. We're still in the realm of equilibrium thermodynamics or thermostatics, right? There is no real processes. There is only equilibrium processes. Remember this? So ultimately speaking, you all know that chemical reactions involve the collision between molecules that possess kinetic energy, and some of those collisions will be energetic enough so that an activated complex can be formed, and chemical bonds can be reshuffled in order to form new molecules at constant number of atoms. This is the underlying condition. But this is really a non-equilibrium process. It's really, generally speaking, a real process, okay? And these collisions will happen at their own rate. And when I say rate, I mean rate of change. So they involve time, okay? They will, for example, occur much faster because of the vibration, okay, the kinetic energy, the mean kinetic energy of the molecules when the temperature is higher, for example. And we can really relate the reaction rate, the rate at which the reaction will take place, with things like concentration and temperature. But we are not dealing right now with time, with non-equilibrium processes, and with what I just described, which is called chemical kinetics. We are really interested in equilibrium, okay? So what the chemical reactions that I'm going to be introducing today are simply statements, okay, which tell us the proportion, the stoichiometry, okay, to use sort of a word of Greek origin, stoichiometry, okay, with which these species can turn from one to the other, okay? And really the underlying concept that constrains all of the way, the potentially infinite ways, is the fact that the atoms must be conserved, okay? That's all. In equilibrium, in chemical equilibrium, in thermostatics, there is no such concept of rate of change. Okay, we're not interested in that. We're really introducing for the first time chemical reactions as essentially a way to define the proportion in which, for example, two molecules, one of hydrogen, one of oxygen, will form one molecule of H2O, for example. We want to generalize this, okay? So it's really a much simpler concept than what you have in chemical kinetics, where you have actual collisions of elementary reactions, that is, and in fact, think about it. I'll say it right now just as an introduction. When you're actually considering collisions between molecules, you're only really considering two kinds of collisions or events. Well, one is the simple collision of two molecules, right? A bimolecular collision. Another one could be, for example, the dissociation of a single molecule. If the temperature is high enough, a single molecule can break up. That's another event. But really, that's all if you think about it, because what else can you consider? The collision of three molecules. But that's an absurdly rare event if you think about it. Think about how many chances there are that three cars will collide exactly at the same time. Okay? On the other hand, a general chemical reaction, okay, which is a stoichiometric statement between all the different molecules, can involve, in principle, any number of reactions, of species, as long as you're conserving the overall number of atoms between them. Okay, so that's absolutely an absolutely important distinction, okay, that you have to have in mind. So let me introduce the notation. So we're going to start with what we call irreversible reactions. And I'm going to define them in a second. And let me just introduce the notation. So I'll write it first and then I'll explain it to you. Okay. So our chemical system, first of all, let me explain what the M's are. Our chemical system will be composed essentially of chemical species, okay, that in general, I'm going to call, in a completely generic way, M1, M2, M3, MNS. NS is the total number of species that I have in my system, okay, NS. So I have a bunch of species here on the left and a bunch of species here on the right. I can write essentially I'll sum from all the species here, both on the left and on the right. So I can add all of the species on the left and all of the species on the right. But the problem is that they appear on the left and on the right with different coefficients. You see here these new coefficients, and I have a prime here on the so-called product side. So we will call the left side the product, sorry, the reactant side. Okay, and on the right side, the product side. And you see that they're different, okay? Now, these coefficients will essentially tell us the proportion in which these species react and disappear or reappear from my chemical species, so from my chemical system. So, for example, this statement here says that, and this is all it says, okay? It doesn't say anything more than this. That for every new I prime moles, okay, of the species Mi, okay, that disappear, that are disappearing from the reactants, okay? So for every new I prime moles of this species here that disappear, this relation tells us that there is another quantity, okay, double prime, new I double prime moles of Mi that appear. That's all it says, okay? So in some sense, what this reaction is a very strict constraint, okay, on the way in which a substance can be transformed, okay, into something else. Before I go further, let me just do an example so that it appears clear, okay? Suppose I have my chemical system, M1, M2, M3, M4, is a very simple system, okay? Hydrogen, oxygen, and water, H2O, okay? So 3 species. So this is M1, this is M2, and this is M3. We will always be doing this numbering of species to make our lives easier, okay? So you'll see that in the future it's going to be very, very useful to do a numbering, okay? So that, for example, this is an arbitrary choice, but you have to, once you make that choice, you have to stick with that choice clearly. So in this case, species number 1 is hydrogen, species number 2 is molecular oxygen, and species number 3 is water. If I want to write between the reactants, that are, for example, hydrogen and oxygen, I will write them this way, for example. 1 mole, okay, of hydrogen plus, now, in this case, I'm writing half a mole of O2, okay? You can't you can't choose these things at random, okay? Plus 0 moles, okay, of H2O, okay? So these are my reactants. So I've also added the product here. Usually H2O is considered as a product, but I'm following this general sort of notation here. So I'm adding all of the species on the left and all of the species on the right, okay? And on the right, I still have the products, but in 0 quantity, so 0 moles of H2. 0 moles of O2, okay, and 1 mole of H2O. So I've set, so for one thing, you've seen that I'm not destroying nor I'm creating atoms, because if you count, and we're going to do this very rigorously later on, but if you count the number of atoms of hydrogen, for example, we have only two hydrogen atoms here, and they're contained in the molecular hydrogen molecule, okay? And you will find them nice and in the same number, okay, in the water molecule here. So we haven't destroyed them. It's not nuclear reaction where we're splitting the atom and creating different new elemental species. We're actually keeping these are chemical reactions. We're keeping the species, the elemental species, completely constant. Okay. So depending on the number of, depending on the initial composition, I'm introducing in the system a certain number of atoms. Okay. Well, at the end of the day, whatever happens to the chemical system, I will always have the same number of atoms. Okay. Same thing for the oxygen here. Half a mole of O2 means that I have just one atomic oxygen mole, and here it is, okay? 1 times, so I have just 1 mole of oxygen, okay? So I haven't destroyed or created anything. Clearly, by looking at these, this notation and this numbering here, well, H2 is my M1. I'm writing it underneath. This is simply the stoichiometric coefficient with a prime here, number 1 for hydrogen. Again, this is Ni prime of species number 2, which is oxygen, M2, and this is Ni prime 3 for M3, which is water. And these are the numbers for these coefficients here on the product side. So double prime, again, 1 for hydrogen, double prime 2 for oxygen, which is M2, and double prime 3 for, sorry, I made a mistake here, for M3, okay? 4 and 3. Now, why are we introducing this sort of general sort of notation? Well, think always, and this is very handy later on, but just try to begin to think of a composition. So I'll always be doing the sort of the R3, okay, the three-dimensional space, because it's the only one I can represent. But suppose that each axis represents essentially the quantity of each species, okay? Then I hope you agree with me that a point, okay? So in fact, I'm not, I'm using another notation, which is the number of moles, okay? N1, N2, and N3, okay? Which symbolically represents species 1, 2, and 3. A point in this space, okay, has coordinates, number of moles of 1, number of moles of 2, number of moles of 3. So identically represents a composition, okay, of the chemical system, for example. Now, what chemical reactions really are, there are constraints on the way this composition can move around in this space. Because really, if I start taking this point and moving it around anywhere, okay, well, what I'm doing is I'm violating the conservation of atoms, okay? Again, the chemical system is a system that you can think of it as a container that I fill with certain initial moles, okay, of substances. The act of doing this will set my initial composition. So for example, say the initial composition is over here. So this will be N1, 0, N2, 0, N3, 0, okay? Now, how do I change the composition so that I can get to here? Well, generally speaking, I can't do it at random. I can't just, go like this, okay? Because if I take, for example, an intermediate composition here and I calculate the number of moles of each atoms, they will be different from the ones I added originally. So what we will see is that, in fact, these numbers here, these stoichiometric coefficients, okay, there's a very definite way in which we can think of them as components of vectors, okay? And the reaction is being essentially I missed this, so as a specific direction, okay? That conserves the number of atoms, okay? And this is what we're going to see later, right now. So this is a constraint on the composition so that you can't just pick any point in R3, but a subset, okay, of points of R3, so that wherever I am in that subset, okay, I will always conserve atoms, okay? And this is what we're going to try and explain later on, okay? So let's go back to our for example, hydrogen, oxygen, okay? So we have understood what the notation is all about, okay? I hope. We have cheated a little bit because we've essentially chosen these coefficients, let's say by eyeballing it, so that it seems balanced, right? There's 2 hydrogen atoms here, 2 here, only 1 hydrogen atom here, and 1 here, okay? I'm taking just half of O2, which means only 1 hydrogen atom. Later on, clearly, we should be doing this automatically somehow. We should be answering the question, okay, but wait a minute, the principle of conservation of atoms is a unique principle. So if you in theory, if you give me all the species present, I should be able to devise a way to automatically find all the possible ways in which these species can react that conserve the number of atoms. And indeed we can, okay? So we won't have to find them by eye, okay, for sure. So what does the statement tell us? It tells us that, for example, every 1/2 mole of O2 that you see disappears from the reactants okay? How many appear? 0. Okay, I can write essentially this for every species, okay? Every 1 mole of hydrogen that disappears, 0 appear, and for 0 moles of H2O that clearly disappear, 1 appears, okay? So what I can do is I can write down the change, okay, in this particular case, the change in the number of moles of each species, okay, which means essentially the final, and well, final is a bad word in thermodynamics. In this case, yes, because in this case, You see, we have an irreversible process. So if we start from here, we know exactly that we're going to end up here. So in fact, it's pretty useless to even talk about an equilibrium condition because we already know what the final composition is, okay? You'll see that real processes, not real processes, but actual stoichiometric reactions are reversible. So the final composition minus the initial one, which we called Ni0, okay, is actually equal to the difference in the stoichiometric coefficients. Okay, need nu I double prime minus nu I prime. Okay, so obviously, for example, in this case, if I choose species number 2, which is oxygen, the change in the moles of oxygen, well, I start, I end up with 0 moles, okay, in this particular case. And I started with half a mole, so the change in moles is always minus a half. Bear in mind that implicitly, in this particular case, I've chosen the initial number of moles exactly equal to my stoichiometric coefficients, but I don't have to do that. Okay. I could choose, for example, the initial number of moles, for example, of oxygen as being 10 moles. Okay. It always means, however, whatever the choice of the initial number of moles of oxygen is, the chemical reaction here always tells me that delta N2 must be equal to minus 1/2. Okay, so if I'd started with 10 moles, in fact, really what this means is that the final composition will have 9.5 moles of oxygen. Okay, minus 10. Okay, this is minus 1/2. Okay, so I will have at the end of the day excess oxygen here in the product side. Okay, I could even write it down. For example, if I still have 1 mole of H2, okay, plus 10 moles of O2, plus, well, oops, plus 0 moles of H2O, okay, I will end up, well, this hydrogen here will still be reacting with half a mole of oxygen to produce, to disappear completely, 0 moles of hydrogen. And only half a mole will still have reacted with H2. So here I have 9.5 left. Okay, so this is called a very oxygen-rich condition, or fuel lean condition, meaning that there is really a deficit in fuel. So you end up with a very, very sort of oxidizing atmosphere at the end of the day. And you still have the production of 1 mole, okay, of H2O. Okay. So in this case, we had this initial composition: 1 mole of hydrogen, half a mole of oxygen, and 0 moles of, this is a half, 0 moles of water that will transform to 0, 0, 1. Okay, this is Ni. Okay, my final composition. In this particular case, I still had 1 mole of initial hydrogen, 10 moles of oxygen, 0 moles of water. So this is my, again, my N0, and I will have essentially 0 moles of hydrogen, 9.5 of oxygen, and 1 mole of hydrogen. Okay? So really what we said is that for these particular reactions, okay, the change in the number of moles is always equal to this difference in the stoichiometric coefficients, okay? But this is a kind of a boring situation, okay, these irreversible reactions. They only go one way. We always know what the final equilibrium is. And if you think about it, if we know what the final equilibrium is, then why have we bothered looking for an equilibrium condition to start with, like minimum of Gibbs energy, because we know it already, okay? Well, but this is not what happens in practical life, okay? In practical, situation, you have what we call reversible reactions. Okay, so in fact, you have two processes, okay, with the same kind of notation, the same kind of reaction. So let me write it again. Okay, you have the forward process, which we saw before. But now you also have the reverse process, okay? So you have to think of this as a dynamic kind of process. You have essentially, well, in the case of what we had before, so imagine this missing, okay? You have what? Well, you have this reaction, we say, completely shifted towards the right, okay? Well, indeed, there is a limit to how far right you can go, because look at this guy here. Well, you only have 1 mole of hydrogen to react with the oxygen. Okay, so at some point, when you're going all to the right, well, you will end the overall hydrogen content. Okay, so this is called a limiting reactant situation, where essentially you just added 1 mole of hydrogen. So that's how far you will go, okay, towards the production of the products, which is water, okay? You can't have negative hydrogen, okay? Obviously, you finished all of your hydrogen to react, so this is the left, sort of the rightmost, point that you can go towards the products. The same thing applies to the left process, to the reverse process, where you're actually favoring the production of reactants. So you're going back here. So it would be a sort of a dissociation of water, if you think about it, in the production of hydrogen and oxygen. But you will stop going to the left when really you run out of water. Okay, you can't produce more hydrogen and oxygen out of thin air. Okay, you have to have molecules of water to start with. Okay, so the truth of the matter is that, well, we have a leftmost and a rightmost limit. Okay, which kind of limit these kind of reversible reactions. Okay, I will rigorously define those through the definition of a progress variable. But I'd like you to think that the equilibrium point will be somewhere in the middle, okay? So somewhere in the middle, okay, where you don't have, for example, zero products or zero reactants. You could in theory, but you have a little bit of all of them, again, in a composition that guarantees the conservation of atoms. That is where you're going to have your equilibrium, meaning that for that and only that composition, the Gibbs energy at constant temperature and pressure will have reached a minimum value. Okay? So this is a far more interesting problem, actually. Okay? Suppose that I can write down for this chemical system the function G, okay? Well, I can then minimize it somehow, okay? We'll build a theory now, but I can minimize that and find my equilibrium composition. So I will find how far right or left the system will want to go spontaneously, okay, by its own, so that the Gibbs energy is minimized, okay? Again, if you want to think again in terms of entropy, you can, okay? Gibbs energy is not really as intuitive now as thinking of entropy as number of configurations. Remember the sheep, okay? Why does the system drive itself towards, it doesn't know anything, okay? It's not an intelligent being, okay? Why does it drive itself towards equilibrium? Simply because it's more likely, okay? The number of configurations at that particular point is much higher than the rest. So it's because there's so many molecules, you can be pretty much guaranteed in terms of probabilistic considerations that the system will drive towards whatever is more likely for it to go, okay? I mean, again, you could also think at one point, one particular configuration is for all the air molecules in your room to escape out the window. That is surely one of the possible configurations. If you calculate how likely that configuration is energetically, there will be hundreds, not hundreds, but of the order of 100, or even more, actually, orders of magnitude difference, okay, between the most likely configuration where you have essentially a uniform pressure field of molecules within your room, okay? So always have this sort of, at the back of your mind, this kind of statistical mechanics kind of vision, okay, or understanding of what we're dealing with here. So what does this say? It's still a statement whereby for every new I prime moles of Mi disappearing, we have new I prime, double prime, sorry, of Mi appearing, okay? But now you can also add and vice versa, okay? For every new I double prime of Mi, okay, disappearing, you still have new I prime of Mi appearing, okay? Okay, let's see how we can sort of rationalize this thing of saying that the composition can be shifted completely to the right or to the left or in between, okay? I need some sort of independent variable, don't I? Some sort of, I like to call it a slider, okay? You know what I mean by slider? Some sort of, you know, when you have a volume kind of control in your stereo, okay, you can go all the way to the left and all the way to the right, right? So suppose that I have here, this is my limitation, okay, in the sense that I can't go any further. And I have a way of measuring this through a variable, which is psi, which changes from a leftmost to a rightmost value. So I have a variable psi which changes in this domain, in this interval, where L and R simply stand for left and right. Can you still hear me? Hopefully.
Yes, Professor.
Yes,
So
bro.
left and right, okay? I can't go any more left than psi L, and I can't go any more right than psi R. Why? Because, well, if I go all the way to the right, then some of my reactants have been depleted completely, okay? So there is no more reaction that can take place. Same thing here. If I go all the way to the left, I have some products here that are completely depleted, 0. So I can't go negative. Remember this, okay? So if I go back to some here, to this representation, well, you have to look at these walls, okay? For example, if you look at this wall here, it means that N1 is 0, right? So this plane here is N1 equals 0, okay? And you can't go any further than that. You can't kind of go through this wall, because then you have unphysical compositions. You have negative compositions that you cannot have, okay? So indeed, if we move along a line, and we'll prove this rigorously later, well, when the line intersects these walls, then that's where you know that you've reached psi L or psi R. Okay, so your slider essentially will move. Let's say it's here. Oops, here and here, for example. Okay, you can only move between this point here and this point here. Okay, you cannot break the wall and go through, clearly, because otherwise you're going to have a negative concentrate or a negative number of moles, which doesn't make any sense. Okay. So how do we define this this slider? Well, we've just said that in the case of irreversible reactions, the difference in the number of moles, the change in the number of moles, is equal to the difference in stoichiometric coefficients. Now, if we normalize the difference in number of moles, and the change in number of moles with the difference in stoichiometric coefficients, then we have our definition. Okay. Okay. This will appear clear in a second. So for every every species, we define essentially this ratio, and it's always going to be equal to, it's always going to be a constant ratio, okay? Because that's exactly what the stoichiometric relation is telling us. So the definition of progress variable is essentially Ni delta Ni, which is Ni minus Ni0, the current composition corresponding to a certain value of psi, minus the initial composition divided by or normalized by the fixed value of this quantity here, which is the difference in the stoichiometric coefficients, okay? And this is valid for all species, so for all I, okay? So again, remember that Ni is our current composition, so depending on where I put my slider, okay? You see, it's linearly related to psi. It could also be, for example, the equilibrium composition. At this point, for example, I'll write it here. One of the most special equilibrium, the most special composition is the equilibrium composition. So if I, sorry. So I can also define, for example, an equilibrium, okay, value, which is, I don't know, somewhere here or here, I don't know, will be Ni of equilibrium, okay, minus Ni0 divided by, again, the difference in stoichiometric coefficients, okay? But in general, any composition, okay, can be generated by just changing this independent variable, okay? In particular, when psi equals 0, look, you see that the composition is equal to the initial composition, okay? So this is always true, okay? When psi equals 0, this is the number of moles of any species is equal to the initial one that I put in, okay? And then again, as I move towards the products, okay, at some point, one of the species will be 0, okay? Then you're going to have to stop, okay? Again, for the leftmost value. How to find these leftmost and rightmost, we'll discuss later on. But the interesting aspect here is that now, through this definition, I can really express my composition uniquely in terms of psi. So my current composition is the initial composition plus this coefficient here, the difference in stoichiometric coefficient, okay, times psi, okay? If I want to consider an infinitesimal change in composition, I just derive this relationship. This is a constant. So again, this will be simply ni I double prime minus ni prime d psi. That's all it is, okay? Now, let me continue with this. There is a special case, for example, where special choice of N0, the initial moles. What if I choose the initial moles as being exactly like the stoichiometric coefficients, okay? Nu I prime, okay? It's a little bit like the irreversible, if you look back into your notes, the irreversible hydrogen-oxygen case that we saw, the very first thing that we saw, okay? Well, now using this expression here, the number of moles, okay, at any point in the reaction is ni I prime plus ni I minus nu I prime psi. So essentially, when psi equals 0, okay, then the composition is equal to, well, the initial composition, which is nu I prime, okay? So essentially, look, there is, because the composition here is equal to the initial one, there is no change in composition, clearly. As we said before, essentially, you're starting, it indicates the fact that the composition is equal to the initial composition, okay? Now, because clearly all of the number of moles are equal to nu I prime, you can say that this is where, if these are reactants and these are products, okay, or left and right, the reaction is completely shifted to the left, meaning that no product is actually formed. We're staying with whatever we started with, okay? We're staying to essentially the current composition as the prime one, okay, the one being completely on the left. So this is when we say that the composition is the reaction is completely shifted to the left, okay? On the other hand, if psi is equal to 1, you can see that Ni is equal to, look at this, so we have Ni prime, nu I prime, and then double prime minus prime. So the composition is the final one, okay? The one appearing on the product side. So over here, okay? So you've shifted completely, okay? Now the reaction towards, yeah, I mean, these should be straight lines, but towards the right side, okay? Again, the composition here on the left side is ni I prime, and on the right side is ni I double prime, okay? So you see now that you only have products here with these with this composition, with this number of moles, okay? Now, this is a very special case where psi essentially varies from 0 to 1, where 0 essentially is, you start from reactants here, and the whole thing is essentially doesn't move anymore, and it's all shifted towards the left, favoring the reactants. And then psi equals 1, it's just products, okay? But this is a particular choice where you essentially have chosen the initial composition as exactly equal to your coefficient, your stoichiometric coefficients. This is not generally not the case, okay? And we will see that in general, the leftmost value is not 0. It can even be negative, okay? So psi L, the leftmost, and psi R is generally not 1, okay? But there are, okay, these leftmost and rightmost values. You can, to familiarize with this, you can go back to a simple hydrogen-oxygen system, okay? Now we have a reversible reaction, and you can define now using the definition of progress variable. It's also called the degree of advancement of a reaction, or progress variable. So that as it increases, moves beyond 0 psi, essentially you're seeing this reaction moving from left to right. That's how you have to look at this. So again, here you can define it either with the hydrogen. So in this particular case, you have the delta N of hydrogen, the variation of moles of hydrogen, based on whatever initial composition you have, normalized by the difference of stoichiometric coefficients. In this case, it's 0, because Ni double prime 1 is 0, so 0 minus 1, which is this coefficient here. Again, this will be for oxygen NO2 minus NO2 prime, sorry, 0, divided by, in this case, 0 minus a half. And for the product, it would be the change of moles, okay, with respect to the initial composition divided by, again, 1 minus whatever stoichiometric coefficients of water is here, which is 0. So you see that now Xi is essentially what Xi is the change in number of moles is the numerator of hydrogen, okay, with a minus sign, okay, meaning that essentially, and the same thing here, okay, the only thing now is that this minus a half becomes minus 2 delta NO2. So you see what's happening here. Let me finish this by writing delta H2O. Sorry. Delta N H2O. Okay. So let me see let me tell you what's going on here. So you see essentially that as Xi is increasing, because of these minus signs, okay, the variation of the number of moles of reactants, well, first of all, it's opposite to the variation of number of moles of the products, clearly. Okay, so in the sense that as Xi increases, the number of moles of products of reactants decreases and the number of moles of products increases. Okay, and you can define this for every species simply because you've integrated the proportion with which they vary. So in this sense, you see that the variation of the number of moles of hydrogen, okay, is twice that of oxygen, okay? Because we need 2 molecules of hydrogen for every molecule of oxygen, okay, in this proportion here, okay? Again, you can see that Xi is 0 at the initial composition because N will be equal to N0. You can also see that, for example, the leftmost value when the whole thing is shifted towards the left will correspond essentially to a situation where the number of moles of water will be 0. You can't go any more left than when the water here on the product side is 0, because otherwise this will start going negative. Same thing for the rightmost value of Xi, okay, the most positive one, because essentially you're favoring H2O until either oxygen or hydrogen is completely depleted. Now, we don't know which one will be depleted first because essentially I haven't given you the initial number of moles, okay? Let me try to finish this. Let me give you a graphical interpretation of this, okay? So remember the ordering 1, 2, and 3 for hydrogen, oxygen, and water. Well, N1 will be equal to N1, 0, okay, plus essentially Ni double prime 1 minus Ni prime 1, et cetera, right? And oops, and we can write this for N2 and N3, okay? So really, we can also have sort of a vectorial, okay, representation, okay, where n vector has components n1, n2, n3, and 0 vector has component n1, 0, n2, 0, n3, 0, plus a vector Ni here times psi. And this vector here will have components the following, right? Et cetera. So the difference in the stoichiometric coefficients for species 1, 2, and 3. Okay? Now, keep this in mind because this will live, essentially, this vectorial representation will live in our phase space, okay? R3 or whatever it is, okay? And it will come in handy in essentially visualizing it geometrically, okay? Suppose that we're starting with, as we did before, with N0, okay, coinciding with essentially all the Ni primes, okay? I will not be able to do this vectorially. So again, we're looking at this reaction here, okay? Suppose that the initial moles are simply 1.5 and 0, okay? So N01 is 1, okay? So the initial number of moles of hydrogen, the initial number of moles of oxygen is 1/2, and the initial number of moles of water, that's 3, is 0, okay? Then I will apply these equations, this relationship, and I have that N1 is equal to 1 plus the difference in hydrogen here is 0 minus 1, so it's minus 1 times psi. N2 is 1/2, and so that's N2, 0. And then the difference between stoichiometric coefficients is minus 1/2. And for N3 is simply 0 plus 1 psi. Okay? So you see now that we have essentially very easy representations, okay, in, for example, this graphical setting where you have on the x-axis the variable psi, which, as we said, varies from 0 to 1, okay? When psi is 0, you only have reactants, okay? And you have essentially the initial composition of hydrogen and oxygen. And you have, in particular, 1/2 mole of oxygen. And so N2, which is NO2, now I can't go straight here. Well, if I graph this particular function here, it's linearly decreasing until we get to this point here, okay? And when psi equals 1, we have depleted completely the oxygen. Now, this is NO2 or N2, as we called it. This is the same thing for hydrogen, okay? We're starting from 1 mole when psi equals 0, and then we'll get again to complete depletion. So they deplete at the same time when this is shifted completely to the right. So that's essentially N1, which is hydrogen, okay? And for water, and you see that the rate at which these two get depleted is double the other, okay? So the hydrogen depletes twice as fast as oxygen. And as far as the water is concerned, simply this linear reaction, oops, well, that's really a shame. I can't draw straight lines. Whatever, okay, you know what I mean. And this is NH2O, okay? So again, and I'll close it here, you see psi changing from 0 to 1. If you have any intermediate value here, psi, this is your composition, okay? And for today, I think we can stop here. And next time I can give you the general case, and then I will give you a more of a geometric representation in terms of vectors, which is far more, I think, tractable. Okay?
Excuse me, Professor.